Welcome, everyone. It's a pleasure to welcome Jelena Diakonikolas at the University of Washington. Jelena is an assistant professor at University of Wisconsin-Madison. She's a PI in one of the peer foundations of data science nodes from the Institute of Foundations of Data Science. She graduated from Columbia, and she did a postdoc with Lorenzo Regia, and then another postdoc with Mike Jordan at Berkeley in another Foundations of Data Science Institute. Jelena has done fantastic work in Nonsmooth and accelerated optimization over the years, and has written crystal clear papers with very generic proof techniques to prove convergence of algorithms in many senses for non-smooth optimization, accelerated optimization, convex optimization, and even sampling. And so it's a pleasure to hear Jelena's latest work today.
Thank you very much, Said, for the very kind introduction. It's a pleasure to be here, and the work I will talk about today is something that just got completed and posted to the archive less than a month ago. So it's a pretty new work. This is the first time I'm talking about it. So you'll forgive me if my delivery is not perfectly smooth or if there are some typos still in the slides. I was just very excited to share the result with this audience, especially since there are many experts in non-smooth optimization who are here at the University of Washington. Now, Zaid warned me that not everyone who comes to this seminar works in optimization, and that I shouldn't assume too much. So I'll start with a very high-level introduction. So we have an optimization problem that I'll write in a generic form, where we want to minimize some objective function over some feasible set or constraint set. And what the feasible set is, I'm not too worried about in this work. We'll just assume it's simple enough. The more interesting stuff will happen based on what we are assuming about the objective function. Now, of course, optimization problems, even if you don't work in optimization, you cannot avoid them, right? People these days like to motivate everything through machine learning and deep learning and LLMs, but we have been using optimization for many things for many years, from stock market over engineering to networking and data centers, medical analytics, weather forecasting. Nature is actually a prime optimizer. There have been papers that show that how slime mold moves in a maze actually can be described by using a certain greedy optimization algorithm. Then there are your classical examples like medical imaging, business analytics. This is a very cute one. There is a group from UW-Madison that reached out to me some months ago, and they manage the largest neutrino detector that's on the South Pole. And guess what? They are solving a certain optimization problem in real time. A very simple one. Non-negative least squares problem, linear least squares problem. But apparently it's consuming more than 50% of their compute power, and they cannot so easily bring more computers to the South Pole. So I have started working with them on developing faster algorithms. Not what I'm going to be talking about today. I just want to mention how pervasive these things are. Now, there are some optimization problems that we consider easy, and people like Cauchy and Newton knew how to solve, and we still use algorithms named after these people. And usually when we think about optimization problems that are easy, we think about functions that are kind of nice and smooth and nicely rounded. But then there are some problems that are really hard. And normally when we imagine those problems, maybe we think about many local minima, but more importantly, a function that can change quite abruptly. Right? And to understand formally what kind of continuous optimization problems are easy or hard, we study them through the notions of complexity of optimization, right? They provide us with a formal model of understanding how things work. Now, when it comes to complexity of continuous optimization, there are some complexity results that are even more like theoretical computer science. There are some problems that are NP hard or PPAD hard that fall into these complexity classes. But more commonly, they are studied in the Oracle model of computation. And this type of study of continuous optimization started with the work of Nemirovsky and Yudin in the late 70s, early 80s. But I think that most of the credit for laying out the foundations of Oracle complexity theory of continuous optimization should really go to Arkady Nemirovsky and his lifetime work. Like many of the results that we have there are really entirely due to him. So what is Oracle model of computation? In the Oracle model, we have our problem that we're trying to solve, and there is some all-knowing Oracle. So what we do is we pick a point, x, usually from the feasible set, but from the vector space where the variables live. And the Oracle returns to us some information about the problem that is related to this point x. Okay, and the most basic examples would be to tell us what the value of the function is at that point, or what the value of the gradient of the function is at that point. Gradient, high-dimensional derivative. Okay, so this is still quite high level. We'll make things a little bit more specific. This particular example is actually what I'm going to be focusing on for most of this talk. And these days, especially when it comes to large-scale optimization, this is a pretty good model to think about. Now, when it comes to how we measure complexity of a problem class, well, in continuous optimization, there are very few problems we can solve to zero error. Usually, we can only solve them to some finitely small error. So there is going to be some target error epsilon. And the way we would measure complexity is we would look at a specific problem class. Problem class is defined by assuming something about our problem. It's necessary. And we look at how many Oracle queries would the best algorithm need to ask on its worst case problem instance to get an error at most epsilon. And for problems like convex optimization problems, the notion of error would be the optimality gap. For non-convex optimization, it would be usually the norm of the gradient or the slope of the function. But is the definition clear? So it's kind of a min-max characterization. Look at the best algorithm and its worst case instance. Okay? Okay, so this was my very quick and hopefully gentle introduction to Oracle complexity of optimization. What I want to do next is review some of the classical results before I get to my results. Before I do that, are there any questions? And I just want to get a sip of water. No? Okay. Okay, so going back to the Oracle complexity model, the specific type of the Oracle that is studied in the Oracle complexity of optimization is called the local Oracle. So what does local mean? In the local Oracle complexity model, when we talk about complexity of classes, we usually assume that we are querying points that are within the feasible set. Remember this. It is going to be important towards the end of the talk. Okay, and then what we get back is some local information about the problem pertaining to the point x. So what does local mean? It means that if you are querying two functions that agree in the neighborhood of the point, then you should be getting the exact same information. So things that would be local are the function value, the value of the gradient if it exists, the value of any higher order derivative if it exists, Taylor approximation of the function around the point. But it cannot be something that is far away from the point. OK. So I mentioned that these Oracle complexity results are normally stated for certain problem classes. So how do we define these problem classes? So first of all, we will either talk about convex optimization or non-convex optimization. For the majority of this talk, I will be talking about convex optimization. Convex optimization, all local minima are global. We can actually bound the optimality gap. So things are good. We normally require certain assumptions about the regularity of the function. Some assumptions are needed. If you're not making any assumptions, you cannot say anything really about the complexity. Now, the required assumptions will normally bound something about the growth of the objective function. So the standard assumptions would be that the objective function is Lipschitz continuous, or that it is what is known as smooth, meaning that its gradient is Lipschitz continuous, or it's higher order smooth, meaning that the Hessian of the function, which is a second order derivative, or even some higher order derivatives, are Lipschitz continuous. So in a sense, you need at least one of these. OK? There are some optional assumptions we sometimes make that bound the growth of the function below. They're optional in the sense that we can get concrete complexity results without them, but when they hold, we get better bounds. Things like function being strongly convex, meaning it grows at least as fast as a quadratic, or being uniformly convex. This just generalizes the growth to a different polynomial function, or satisfying some local growth conditions. There are conditions known as PL condition or sharpness and so on. Now, when it comes to these standard problem classes, the complexity of optimization is very well understood in the sense that we have matching upper and lower bounds, both for convex optimization and for non-convex optimization, for various settings. And this is just a subset of work. There are like over 4 decades of papers that are studying different variants of these problems for these standard problem classes. Now, I want to give you just a subset of those complexity results for 2 specific classes of problems, and just tell you what they are. OK? And these complexity results, even the lower bounds, they appear even in the Mirovsky and Yudin book, 1983. OK, so the first class I want to mention is the class of non-smooth convex optimization problems. Usually when we study these problems, we look at ball. Normally a Euclidean ball. For this talk is enough. Function is L Lipschitz on that ball, convex, and the diameter of the ball is D. We have a target error epsilon. So to get to an optimality gap epsilon, this many queries Oracle queries are needed, upper and lower bound. Any local queries for the lower bound, and in fact, first order queries suffice for the upper bound. D here is the ambient dimension. This part is what I want to focus on, the part that is essentially that is independent of the dimension, something that would hold for high dimensional problems. Also, the algorithms that we have that achieve this are much simpler than the algorithms we have that achieve this. This has very simple iteration. This has like d cube iteration with ellipsoid. Okay, so what changes now when we go to our next class of problems? So the next standard class of problems is smooth convex optimization. Still have a convex function, same diameter of the set, but now the function is L smooth, meaning that the gradient is Lipschitz continuous with constant L. Okay? Oracle complexity very well understood from the aspect, so matching upper and lower bounds are of this order. So we had on previous one L squared D squared over epsilon squared. Here we have square root of L over epsilon times D. So much lower. Okay? And the motivation for this work was basically what lies in between. And I'll get more to that, but before I do, I would be remiss not to mention some in-between models that people have considered. Okay, so these are the classical results for classical problem classes. There are different models that have been considered in the literature. So for example, assuming that the function is globally Lipschitz is not required, one can assume some notion of local Lipschitzness. Basically, if your algorithm iterates are all going to be on a compact set, well, you only need Lipschitzness on that set. So you can get a better constant. It is possible to sometimes even go beyond non-smooth, non-Lipschitz problems and reformulate them in a semi-generic way to Lipschitz ones. But to make and I was actually confused by these results for some time, but actually to make them interpretable, one still needs some kind of upper bound on the growth of the function between the initial and the target point. There are classes of weakly smooth functions that have been introduced to interpolate between non-smooth Lipschitz and smooth functions. So basically, smoothness is Lipschitz gradients, Lipschitzness is bounded gradients. So in between, you can interpolate with the holder condition that looks like this. So kappa is going to be between 0 and 1. If you put 0, you recover bounded variation of the gradient, which is like Lipschitz functions. When it is 1, you recover smooth functions. Okay? These have been studied as a global property to interpolate between these classes in papers by Nestrov, but also in some other works. Another way to try to go beyond these general problem classes has been by assuming we have stronger oracles that are not necessarily anymore just these local oracles that I talked about. One very common example is something called the proximal oracle, studied in the work by Rockefeller. I mean, these are classical results, also work by Guller and many, many others. The other type would be if a function can be expressed as in a min-max form, so you can separate things like nonlinearity and linearity and max of smooth or non-smooth functions. In this work, I will not be assuming access to any type of stronger oracle. And in fact, we're not going to need any of this, but as a special case, we will be able to recover optimal results, for example, for this class of problems. Now, what is important about all these existing bounds and what they do not capture, and what is kind of the main thing that motivated this work? And the best way to get the intuition is by looking at the picture. And please ignore this top part. This is me not knowing how to plot well in Matplotlib. I want you to focus on this part here of the function in here. So which one would you say is more non-smooth? The left one. Why? It's pointier at the bottom. There is a sharper transition between the slope in this one. This is the basic definition. Classical complexity results will not distinguish between these two functions. So both these functions are Lipschitz continuous with the same Lipschitz constant. But even intuitively, when you look at them pictorially, this looks like a smoother function. And both are piecewise linear, so they're both clearly non-smooth, but somehow this one seems more controlled. We should be able to do better on it. Now what is happening when we look at these functions, and why do we say that this one was less non-smooth? Well, if you were to smoothen this function, how would you smoothen? You do some local averaging of the function. You keep the same scale, and you look at how far is the smoothed version from the original one. Well, it remains quite close. Whereas if you do the same for the other function, well, this distance seems bigger than this one. And things become much more pronounced, as you go to higher dimensions. Okay? So this is the first thing that's not really captured by the things that we knew before. The second thing is that even though the function is non-smooth, it's not clear your algorithm would even realize that. Because if you run things like, this is just gradient descent, you see the algorithm goes over this ridge, it doesn't even realize there's anything going on. Because your algorithm is going to be taking some discrete path, and it only sees the function on that discrete path, and there are many ways to connect the dots. So for your algorithm, there is not necessarily a big difference between a non-smooth and a smooth function. So how do we even capture this? And what is the key property that should tell us more about complexity? So that's what I'm trying to get at. And the claim I would like to make in this talk is that what matters is how the gradient or subgradient or the slope of the function changes over small regions. This is the work I said. It was just posted less than a month ago. It is joined with Cristobal Guzman, and it is currently on the archive. Okay. Any questions before I get to the next part? Okay. So let me give you some intuition before I state formal definitions. Okay, so when we try to think about a function being close to smooth, the way we understand close to smooth is that these ridges or kinks, like where the function bends, are not too sharp. They're kind of mild. Okay, so pictorially, if I was to look at some small region and look at the slope of my function over that local region, there shouldn't be any large change in the slope. Okay? There are some technicalities I need to go over before I give you the definitions. So in this work, we always assume that the function is locally Lipschitz, meaning that on every compact set, there is some finite Lipschitz constant. Doesn't matter how large. The results don't depend on it at all. The reason is that we just need to ensure some technical conditions. I think absolute continuity would suffice, but basically, you want to ensure that the function is almost everywhere differentiable, and things like the first theorem of calculus go through. Those are the things you need, and why we assume this. It's just sufficient for that. And because the functions we work with are potentially not differentiable everywhere, okay, there may be some points where they're not differentiable. We just use gamma f of x to denote one subgradient of f at x, so one of these lower bounding hyperplanes. Doesn't matter which one, just for notational convenience. Okay, so What is the first notion? The first notion talks about the maximum change in the subgradients over small local regions. So we say that the function is grad BMV, which means it has bounded maximum local subgradient variation if there exists some radius r and the positive constant L hat r, such that for any x and y, if they are within a distance r from each other, the change in the subgradient is bounded by this L hat r. And just to remind you, so these are any two subgradients at these 2 points. Is this clear? Is the definition? Okay. So we can think of this as the worst case change or worst case variation of the subgradient over small region. There is a similar notion that was studied in prior work, but not as a local property, rather as a global property, meaning that it holds between any 2 points. Here we are interested just in points that are close to each other. Yes?
Sorry, just for, in this case, when, like, let's say x and y are points, or at least x is a point at which f is differentiable, then the subgradient here would just be the gradient, but I do that x. Okay, so
It's just to account for
possible
where it's not unique, if a function is not different. If you're running any algorithm, you're highly unlikely to query the point that where the function is not differentiable, but still we need to make sure that everything is set up correctly. Can anyone tell me an obvious bound for this L hat r for Lipschitz continuous functions?
L?
2L. 2L, they can be in opposite directions, so the obvious bound, so this is never larger than 2L. So basically, if I recover a complexity result that is the same as the previous ones, and instead of this L hat r, instead of L, I have L hat r, I'm not losing anything, right? Because this is just a constant. But it is more fine-grained because this can be much smaller, and I'll give you examples of that. Yes?
Okay, and then you'll tell me, okay.
Oh, you wanted to see the example. Okay, I want to just state the definitions first, and then I'll go to the examples. Okay. There is a second definition, which is a little bit more complicated, but the way to think about it is the change in the subgradient in an average sense over a region. So fr is the function you would get by smoothing the function over small balls of radius r. Just get it by averaging. What this is talking about, so you have a supremum of rho, supremum over a radius up to r, and then you get the average deviation on a sphere of radius rho. Deviation between the subgradient and the gradient of the smoothed function. So we assume this is bounded. So this notion is inspired by something called bounded mean oscillation. It is a property that is quite heavily studied in harmonic analysis, and it turns out it's also useful for studying complexity, as I hope to convince you. One difference is that they look at the supremum for any positive radius, whereas here we are looking at local properties, so we bound it by r. Okay, and as I said, you can think of it as average deviation of the subgradient over small regions, and it should be kind of obvious that compared to that L hat r, which was the maximum, this LR is always less than or equal, right? Because each individual one you can bound by L hat r. Okay, so now let's go to properties and hopefully gain some intuition. Yes?
So how is this related to, like, assuming that you are in a function class that is Bezoff? So it is related to Bezoff function classes, right?
Oh, I don't know. Let's talk about it later. Okay, so first of all, this is certainly more fine-grained than Lipschitz continuity, right? Because the constants I have shown you are always bounded by 2 times the Lipschitz constant. And potentially they can be much smaller, pictorially, because this change, if you look at a small region, is much smaller than the global change, which can be between any 2 slopes. Now let's see concrete examples, how much smaller. First of all, there are functions that are not globally Lipschitz continuous, but are both grad BMO and grad BMB. So they satisfy this boundedness over local regions of the subgradient. The simplest example I can give you is a function consisting of 2 pieces. So it is constant when the norm is bounded by 1, and then it grows like a quadratic. The function is continuous, but the gradient has discontinuity at these points here. So clearly it cannot be smooth, or even weakly smooth. Right? It would need to have at least continuous gradient for that. The function is not globally Lipschitz continuous because if you are in the place where it is quadratic, the gradient is 2x, so the norm is unbounded. It is locally Lipschitz, but the local Lipschitz constant scales with the diameter of the set. Well, it turns out that if you take, you can take r less than 2. That doesn't even have to be less than or equal to 1. Both of these constants are bounded by 2. Anywhere you look at this function. And a nice thing is that if you are looking at this property as opposed to Lipschitz continuity, you can allow quadratic growth. So people who have been in the MLOpt community for some years now know that for a while there were these papers that would assume that the function is both Lipschitz continuous and strongly convex and problem unconstrained. And that's impossible, so the papers would get automatically rejected. But had they instead assumed something like this, there would be no contradiction, and it's still meaningful to study those problems. Okay, so both are fine-grained. More informative, I think we can agree on that so far. As long as I can state complexity results in terms of these 2 constants. Okay, the other example is that actually how the subgradient changes in this average sense can be much smaller than the worst case one. In other words, this LR can be much smaller than L hat R. Here's an example inspired by geometric properties of high-dimensional sphere and ball from Foundations of Data Science book, chapter 2. It's a very well-studied property, and you'll see why. So the setup is you have a function that basically only depends on 1 coordinate. It's equal to 0 in some region, and then it just grows linearly. Okay? Clearly 1 Lipschitz function. Everyone agrees with that. Okay? If you take R large enough, the L hat R is going to be basically determined by these 2 planes, and then it's going to force it to be 2. Okay? So let's take a specific C, which is going to be scaling with root D. D is the dimension. This still remains 2. I'm not going to show you the entire calculation for LR, but if you do a little bit of basic calculus, you can show that it corresponds to this integral. It's just you integrate the sphere in the intersection of x1 being greater than c over root d minus 1. Does anyone know how small this is? Whoops, I kind of showed it. It's bounded by 2 over c e to the minus c squared, which for this choice is exponentially small in the dimension. So you can have this LR be much smaller than L hat R. Now, of course, like this seems like an extreme example, and it is an extreme example because I wanted to have something that I can calculate well, right? But you can rotate this example any way you like. Get that the function depends on all the coordinates, but it's just a change of basis, right? The true dependencies in a small dimensional space and have the same conclusion. Or depend on a constant number of coordinates, and you would have a conclusion. Okay, any questions about this? So far, so good. Yeah?
I don't know how your bounds will look like, but I'm curious, like if say LR comes into the picture in the bounds, and if this is like exponentially small, then like what is the number of steps that will be required? Like will it be like constant or very small?
Potentially. The main thing is that we don't know how to detect that, but from the aspect of complexity, yes. As it should be, because true problem is low dimensional.
I'm just curious, this is like naively maybe like a common example of this problem would be if you're looking at an expectation of non-smooth functions, which is smooth. But if you sample from the distribution, you get something non-smooth. So in that case, so is that something you looked at? So in other words, like do those, in other words, the larger the sample, the closer your function is to being smooth, but it's never smooth. So that should satisfy your condition, I assume. Like imagine.
I'm not sure I'm fully following, but so you're saying?
So take an expectation of a non-smooth function.
Okay.
Then typically that's going to be smooth.
Okay.
But now suppose I take an empirical average instead of the expectation. It's always non-smooth. But I think that should satisfy your condition.
Probably, yes. We haven't looked at that specific example, but I think that would be...
Like you can then learn to get better estimates for minimizing functions, from non-smooth functions, from finding many samples that are smooth in expectation.
I would think so. And I think you'll see why when I show the complexity results. Potentially, at least. Okay. Okay, so let's see the results for convex optimization. Okay, so let's say we have a function that is convex and satisfies this grad B and V property, which, to remind you, is the bounded deviation of the subgradient in the maximum sense. At some radius, R0, as long as it's non-zero. Given any target error epsilon, there is an algorithm that you can run. And the algorithm can guarantee, basically, that for any R and the associated L hat R, you get a point xk that has this target optimality gap with this many oracle queries to the function. Okay, so this part is what we expect from non-smooth optimization. But you have L hat R here, which can potentially be smaller. This part is generally going to be dominated by this one. In fact, for any Lipschitz function, this is going to be dominating, and it calls for any R. So you can choose it any way you like. In fact, if you now try to specialize results to the classical complexity classes, like non-smooth Lipschitz, weakly smooth, smooth, you just choose the appropriate R, you plug it into this bound, you're going to recover optimal oracle complexity bound. Okay? The algorithm, in fact, can be made adaptive to the best R. You pay at most logarithmic cost, and it's by a standard backtracking line search type of argument. And now here's the key part. The analysis is actually quite simple. The key property that is used, and I think grad students can do this as an exercise, is that if you have points that are at a distance larger than R, then you can treat your function as smooth just with constant L hat R over R. If they're less than R, this is the best you can say, but there is a way to still bound the error in the analysis. Okay. Any questions about this result? So the average LR doesn't appear here at all. This is just for the maximum one. Yes?
Sorry, how would you pick R to recover, like, for example, the rate for like a beta smooth? Would you pick R equals like epsilon over? You said that this can recover the optimal rate for beta smooth optimization. Like I think
Yes. So if a function is smooth, then this L hat R you can bound by beta times R. Okay, so R and R are going to cancel out here, and you just pick it sufficiently small. Basically, what you do, you pick it to balance out these two terms, and you're going to recover the. And that's what you do for any weakly smooth, in fact. Any other questions? Okay. The second result is obtained using randomized smoothing, which is kind of what even inspired us to look at this average sense and bounded mean oscillation business. So this will not hold for any R. It's going to hold for one specific one. Okay? So if you have a function f that is grad BMO at some radius, let's say that R0 is at least epsilon, then there is an algorithm that for some specific R and these associated constant outputs a point with a target error in the number of iterations that look like this. I'll show you what lambda R is in a second. So now, if this is the term that dominates the complexity, this is potentially smaller than what is on the previous slide because LR can be much smaller than L hat R. Okay. This lambda R, in the worst case, has a dependence on the dimension that is unavoidable. There are worst case instances where you cannot get anything better than at least some polynomial dependence on the dimension. Okay? But, if LR is really small, maybe, these are going to be small, so this is still going to dominate. There are cases, however, where there is no real dependence on the dimension. I'll get back to it in a second, but basically, if around the solution, the subgradient set is simple. What would simple mean? It looks like a polynomial. It looks like a polytope with polynomially many vertices, or there is not too large enclosing polytope with polynomially many vertices. Then this would be log d, square root log d, and you have another square root, so you get log d to 1/4. It's actually important for what we'll go to next. But this bound is mainly going to be useful for the cases when LR is much lower than L hat R, at least in the sequential case. Turns out it's also useful for parallel convex optimization. If you are in the setting of parallel convex optimization, meaning that you can query function at many points in parallel per round, this term is known that you can completely get rid of. The first one you cannot. Okay, so basically this result is obtained as a corollary of the previous theorem. And if you have a function that is grad BMO, or even grad BMD, it doesn't matter, at some radius R0 that is at least epsilon root d, and you assume that the function is well approximated by a piecewise linear function with poly d pieces in a neighborhood of x star, meaning that there is an enclosing polytope for the subgradient. Then for any epsilon, there is an algorithm that queries polynomially many points per round and outputs a point with target error with this many parallel rounds of queries. So essentially, if you ignore this log d to 1/4, this is the square root of the sequential complexity. It's essentially independent of the dimension because, if you take d to be a trillion, this is like 2. So it's a very slowly growing function. Bottom line is for functions that are either piecewise linear or well approximated by a piecewise linear with polynomially many pieces, you can actually get better parallel complexity. Yes?
So in each of these theorems, you have a big O, right? So there's a constant. The constant, it's a numerical value? Or?
It's a numerical value independent of any other problem parameters. So some number that I was too lazy to write.
Okay, but do you know if it's like 2 trillions or is it?
No. The constants for all these results are, 2 or 10, or I don't think they're ever larger than 100. Yes, some reasonable constant. Now, if people have seen results for parallel convex optimization, they would ask this question right away. And in fact, the reason this paper didn't get posted many months ago was that we had a hard time reconciling the result we got with the lower bounds, because the lower bounds for parallel convex optimization, that they tell us that in high dimensions, we cannot improve on the number of rounds by querying polynomially many points. There is a lower bound, even in a paper of Cristobal and mine, that is roughly d to 1/3. There are some more recent lower bounds I didn't state here that improve that to a root d. And they exactly correspond to these functions. And also, so we went back, rechecked these results, simplified the proof in the process, and couldn't find any contradiction. So we went back and read our own paper from 5-6 years ago, and then managed to convince ourselves that there is no contradiction. Another thing is people who are experts also wondered about this. We got an email from Ohad Shamir also saying, hey, like this, it doesn't. Here's what is happening. And this is what I told you at the beginning, that it is important that in local oracle lower bounds, you're querying the point within the set. To get their upper bound, we need to do this randomized smoothing, which requires querying the function at not only a feasible set, but also points that are order epsilon root d from the feasible set. Now, if you are allowed to query points that are at order epsilon root d away from the solution in the lower bounds become uninformative. So basically what is happening, these lower bounds are based on concentration of high-dimensional sub-Gaussian random variables. If you have distance that actually scales with epsilon root d, you lose concentration. They become completely uninformative. Now, what Ohad asked us about was, well, there are ways to extend lower bounds to the entire RD, but the extension matters. This was even in, like those extensions were even in our papers because they extend this piecewise linear function by something that's not piecewise linear. It's a norm. And that norm would not satisfy the property that we need for the improved oracle complexity lower bounds. Upper bounds, sorry. Okay, and I'm just, because I'm getting to the end of the talk, I would just say that even for non-convex optimization, these notions of local bounded subgradient variation are useful. There have been quite interesting papers based on Goldstein's method, including by Dima and Dave McDavis and others. I didn't even formally state the result, but what I want to say is that basically the Lipschitz constant in those results you can replace by this L hat R. And also just by plugging in, you can recover from the same results for smooth optimization and weakly smooth optimization. Okay. So to summarize, I hope I have convinced you at least to some extent that this notion of how the slope of the function or how the subgradient of the function varies over local region is what truly matters for understanding the complexity of optimization, because this not only captures the previous results that were well known in the literature, but also provides us with a more fine-grained understanding of complexity, because the bounds we get can potentially be much lower. They strictly generalize other common classes, so they contain also some problems that are not captured by previously studied complexity classes. And this is perhaps one of the most surprising aspects of the results, because for many years now, people had this strong belief that in high dimensions, we cannot benefit from parallelization in convex optimization, and it turns out we can. We just need to look at the problem a little bit differently. In terms of what next, I actually don't know what is the correct dependence on that LR. In terms of lower bounds, the existing lower bounds for Lipschitz convex optimization would satisfy that both this L hat R and LR are equal to L. But I don't know if it is possible to get a result that's LR squared over epsilon squared, or if there is a stronger lower bound. Another thing that would be interesting to have, so I said we can have this log cost for the first result and have an adaptive method at a logarithmic cost. There is now a growing number of results on locally adaptive methods that don't use any local searches, no line search in them. So it would be interesting to see whether these results can be made locally adaptive. So that's all I had, and I'm happy to take any questions.
Questions?
Yep.
Yeah, Dima?
Can you give a sense of how the algorithms work?
So I'll repeat the question first.
Can I give a sense of how the algorithm works? So actually, some of the algorithms that we already had would work just by adapting the analysis. In the paper, we used an algorithm from my prior work called HD+, because I knew how to set up the analysis so that I could just think about bounding 3 specific quantities and then do the analysis very quickly. But I think basically any of the, or almost any of these universal gradient methods would work just by properly adapting it. And the randomized smoothing, it's just apply the same methods to the randomized smoothing of the function.
And then the non-smooth one, this is the Goldstein's differential shrinks?
The one for Goldstein method is your standard Goldstein method. Because if you even think about Goldstein, it only cares about what happens within this delta ball. So really what should matter is the chain, what happens within that delta ball, and that's what the results show.
Can these complexity results take advantage of like strong convexity?
Can these complexity results take advantage of strong convexity? Yes, they can. I mean, the easiest thing to do would be to infer things just based on restarting the algorithm, right? But there is possibly something more sophisticated you can do. There are results, for example, by Day McDavis, where they were looking specifically at functions that have some local quadratic growth but are non-smooth. That would be interesting to see. We didn't go into that much depth for this work. We just wanted to keep the messages very concise and clear. Yes?
So the prior lower bounds, they kind of existed because you were only allowed to sample from the space.
For parallel, yeah.
So do you analyze like where does the actual transition take place, like when you move away? Like in your algorithm, you're kind of sampling outside the space. So there has to be some transition point, right? Like beyond which the lower bound completely breaks.
Okay, so let me try to repeat this. When we look at the lower bounds for parallel convex optimization, have we looked at where we need to query for the lower bounds to break, like how far from the feasible set?
Yeah.
Well, certainly for epsilon root D from the feasible set. That's, I think, exactly the point where the dimension-dependent part of the lower bound becomes a constant. If you took something smaller than that, you would, I think, get a weaker lower bound, but still potentially dependent on the dimension.
All right, let's thank the speaker again.